In the first two videos, we gave you kind of an overview and history of measurement. Measurement, again, being kind of the foundational approach to knowledge building in science. You have to be able to measure things in order to communicate what you know about them. And so now we're going to get into the application of this. And so we're going to look at what it means to record measurements and to record them to the correct number of significant digits. The thing to understand is that all measurements are estimates. And so what you have to be able to communicate is when looking at a particular measuring device, how well can that device estimate a measurement, and how effectively can you as the measurer communicate that information? Those are really the two key pieces that allow us to determine what makes a measurement a good measurement. How sensitive is the measuring device, and how well can the measurer communicate that information. Remember that all measurements have two pieces. A number, that would be its magnitude, and then a unit. That is the coding of the information that tells you what that number is referring to. It tells you what kind of measurement, length, mass, energy, and it also tells you how big that measurement is relative to the set of units, right? So when we take measurements in science classes, we say that we record all of our measurements to the proper number of significant digits. Sometimes you'll hear this referred to as significant figures. Those terms are used interchangeably, digits and figures. All right, significant digits are all of the numbers in a measurement that are certain, plus one estimated digit. You are only allowed to estimate at one point, and at the point that you estimate, that is always the last digit in your measurement, you can say nothing else about the number part of that measurement. Significant digits reflect the sensitivity of a measuring device. The more digits in a measurement, or the more significant digits in a measurement, the more sensitive the measurement itself. All right, so let's look at how this is done. Here you have an object, so this red bar, we're going to measure this thing using this red bar. Now, on the left side of the screen, we're imagining that red bar going all the way down to 0 on this measuring device. We're imagining the measuring device itself going all the way down to 0. So they're both starting at 0. We're taking the measurement where that little dotted line is on the measuring device. And so when we say significant digits are everything we know for certain plus one estimated digit, we're going to go and we're going to look at this red bar that we're measuring, and we know for certain that thing is at least 2 centimeters, right? What we do not know is that the actual measurement lies somewhere between 2 and 3 centimeters, and without any additional markings on that scale, the best you can do is guess where you think that measurement is. And so I might guess it's 2.5 centimeters. So that measurement would have 2 significant digits, with that 5 being the estimated digit. What that means is that measurement might be 2.4, it might be 2.6. We don't know for certain, but we're guessing it's in the neighborhood of 2.5, right? The 2 we know for certain, the 5 we are estimating on. But here's the deal. If I change my measuring device, right? I'm changing my measuring device. I'm not changing the object. I'm not changing anything else about this measuring process than the number of markings on the scale. Now there's some formatting features going on here, and this dotted line is a little off center, so we might think about that dotted line being in line with that arrow. That's just a formatting bit. But here's the deal. I now know for certain this thing is 2 centimeters. This is 2.1, this is 2.2, 2.3, 2.4, and we know that it is past 2.5. So we know the 2.5 for certain. Now what we don't know is it's somewhere between 2.5 and 2.6, and where do we think that is? If we think it's exactly halfway, then we would call that 2.55 centimeters, with the second 5 there, the one furthest to the right, is now our estimated digit. This measurement now has 3 significant digits because the measuring device is a more sensitive measuring device. Now, if we're looking at the screen right now thinking, well, it's actually, the arrow's a little bit past that dotted line, the dotted line is ill-placed, then you might readjust. You might say your estimate is 2.56 centimeters. Here's the deal. The last digit is an estimate. And so, if you get 2.56, that's every bit a correct answer as someone that says 2.55. If you say 2.51, I'm going to say call your parents and ask for an optometrist appointment because you need to get your eyes looked at. At 2.51 is a bad estimate, okay? 2.41 is a bad measurement because you now have a wrong certain digit. That first 0.5 should be a certain digit. So again, down at the bottom here, we have two significant digits. The 5 is the estimated digit at the top. We have 3 significant digits, and the 5 here in the hundredths place is an estimated digit. Okay. You might think about what this measuring device is. You might think about what units you're going to need. You might want to go ahead and pause the video and see if you can give me a measurement to the correct number of significant digits on this scale. So pause the video, write down a number on your paper, and then turn the video back on and see how you did. No, I mean pause the video. No, pause it. Pause it now. Okay, so if you pause the video and you checked your answer, we know for certain we are at 30 degrees on this scale. That is 40 degrees. So think about what each one of these marks has to be. So if you got 10 marks in between 30 and 40, that's 31, 32, 33, 34, 35, 36, 37. So you know that it is certainly past 36. Maybe not quite to 37, or maybe you think it's exactly at 37. We'll come back there in a second. But if you want to think about this thing as being in between any two marks on the scale, so if that's 36 and that's 37, it's going to take one decimal place to communicate that to your reader. So think about this for a second. If it were halfway between those marks, what would you have to record the measurement as? Hopefully the answer in your brain is 36.5. That means it takes one decimal place to communicate something on this scale. So if we think we are not quite to that 37 mark, you might write 36.9 degrees Celsius. Don't forget your unit. If you don't have a unit, you don't have a correct answer here, okay? If you think it's right on the 37, that's fine. You have to write 37.0 because that tells us our estimate is in that tenths place. And here's the difference. 37.0 means this measurement might be 37.1, it might be 36.9, maybe even 36.8. Just writing 37 without the 0.0 means it might be 36, it might be 37. But looking at this, we know this isn't anywhere near 37. Our uncertainty is not in the ones place. It's in the tenths place. It's between any two marks on the scale. So you can always look at a scale before you take a measurement, and you can think to yourself, what's the smallest mark on the scale? I have to read one more decimal place. In this case, the smallest mark on the scale is the ones place. And so you have to read to the tenths place to get an accurate measurement. All right, let's take a look at these two. These are graduated cylinders. When reading a graduated cylinder, you have to read to the bottom of the kind of curved line of liquid in here. And I want you to think back to your previous science class, see if you remember what that's called, the bottom of the curve in a graduated cylinder. And as you're racking your brain on that, hopefully you came to the word meniscus. Now don't confuse this with the meniscus in your knee. That's a anatomy term. We're talking in scientific terms. The meniscus is the curved surface of a liquid in a narrow container. Okay, so we're going to start with the drawing of the graduated cylinder on the right. And so, again, I want you to think about this measurement. I want you to write it down to the correct number of significant digits. And I want you to pause the video, write your answer on the paper. Okay, if we're going to check your answer now, and if you didn't pause the video or write an answer down, you need to go ahead and do that because you really need to get the practice at this as we move forward. This is going to be the application piece of this chapter. So here we are at 70. Here's 71. Here's 72. Here's 73, right? We're 70 and 80, so each mark is 1 milliliter. Means we're going to read past the 1 mil, or we're going to read 1 decimal place past that. So we have to go to the tenths place. So we know it's right here around 73. If you think it's exactly on 73, you write 73.0. If you think it might be just a little past, you write 73.1 milliliters. You need that tenths place. You need that unit. Now let's look over on the left, because this one is trickier. So if that is 6 and that is 8, think about what this slightly longer line is here. And if you gave your brain time to think about that, that is going to be 7 milliliters. So what is each increment on this scale? So if that's 6 and that's 7, we have to be counting by 0.2, 0.3, or sorry, 0.2, 0.4, 0.6, 0.8, and 7 milliliters. If we are estimating in between these marks, what are we estimating? Well, halfway between 0.2 and 0.4 is 0.3. We're still in the tenths place. That's where the estimation is. But this one is a lot trickier, and you're unlikely to actually see this problem from me on any test. You're going to see things broken down into tens. One of the ways we tell the difference between these graduated cylinders, so let's say we think this one is between the 6.6 and the 6.8, so I might call it 6.7. So notice these don't have the same set of markings on these two scales, but they measure to the same decimal place. And the way we sort that out is through a thing called plus minus or error or uncertainty. The uncertainty for a graduated cylinder is going to be half the smallest marking. So the smallest marking here is 0.2 milliliters. That means our uncertainty is plus or minus 0.1 milliliters. Whereas here the smallest marking is 1 milliliter. Half of 1 milliliter is 0.5. Our error over here is larger because the increments on the scale on the right are larger than they are on the left. Here's another one for you to take a look at. This is a triple beam balance. Here's your hundreds place, here's your tens place on the back, and then your front is the 1 gram slide. And so you have to add all the slides together, right? We've got 20, we've got 0 in the hundreds place, and then the reading is actually taken off this front scale. So you want to read this little mark right here on the scale. So I'm going to give you a second, pause the video and write down a measurement, see how you do. Okay, if you pause the video, we know we're at 20 grams. We know for certain we're at 26 grams if we add those together. That's 26.1, 0.2, 0.3, 0.4. We know for certain we've passed 26.4, and then we have to estimate in between those last two marks. Each mark is 0.1 grams, means you need to read one more decimal place. In this case, 26.45, 26.46. Again, you can be 1 or 2 off in that last digit and still have the right answer. So that is 4 significant digits on this measurement. The estimated digit is the 5, so it could be 26.43, it could be 26.46. That estimate lies there. Don't forget your unit. And that's how you record measurements to the correct number of significant digits.